Here's a solubility question where they're asking us to really get to the heart of the common ion effect. They're giving us a single salt, silver sulfate, and they give us the KSP value, and they say find the solubility of that salt in each of the following solutions: water, a solution that contains a common ion of silver, and a solution that contains a common ion of sulfate. And we're going to be able to draw some conclusions about the common ion effect and Le Chatelier's principle based on this. So the first part isn't going to be too hard. We're just going to start with a dissociation equation, silver sulfate, breaking apart. We do need a coefficient of 2 in front of the silver to make it balance. And in part A, let's be clear that we're working on part A here, we've got a solution of water, so the initial concentration for both the silver and the sulfate is 0. And if we just flesh out the ice table, make sure that you're aware that the coefficient 2 in front of silver means that it's plus 2x rather than plus 1x when making that ice table fleshed out. We'll write an expression for KSP, square the concentration of silver, and then multiply it by the concentration of sulfate. So 2x quantity squared times x, that works out to be 4x cubed, and that's all equal to the given KSP value, which they gave us at the top, of 1.2 times 10 to the negative fifth. So if we pull out our calculator and solve for x, again, they want us to find solubility, so that is find the value of x. In this case, it works out to be 0.014. Now let's compare that to what we have in part B. In part B, we have a solution of 0.2 molar silver nitrate, and when that breaks apart, the silver nitrate, you get 0.2 molar silver ion to begin with. And similarly, when we get to part C, we've got 0.21 molar potassium sulfate. When that breaks apart, we'll start with 0.21 molar sulfate ion. So part B, again, we write a good dissociation equation, and it's going to be the same for all parts of this problem. We'll ice it. And the sulfate is the same as we found in part A, 0 plus x, and you end up with x. But the silver concentration initially is not 0, it's 0.2. We still add 2x to that. And we end up with an equilibrium concentration of silver that's different than what we had before. Don't forget to square the expression when you plug into the KSP value expression. Now, can we make the mathematical assumption? Absolutely. It would be wise to do so. The value of 0.2 plus 2x is roughly 0.2. And then we can just carry on our calculation as before. The value of KSP they gave us, 1.2 10 to the negative fifth, and here we're just solving for x. Go ahead and pull out your calculator, and this one works out to be 3 times 10 to the negative fourth. Okay. Let's do something similar for part C. Start with a good equation. And in part C, the solution was 0.21 molar potassium sulfate. There was no silver in potassium sulfate. So the silver ion works out just like it did in part A, but the sulfate ion is different this time. instead of putting a 0 for the initial concentration, oops, I made a little mistake. The silver concentration is plus 2x, so it ends up being plus 2x. But the sulfate concentration is initially 0.21, and to that we still add x, so at equilibrium we get 0.21 plus x. When we write the expression for KSP, and plug in our values from the ice table, it's 2x quantity squared times 0.21 plus x. We can absolutely make the mathematical assumption to simplify. 0.21 plus x is roughly equal to just 0.21. And since they had given us at the very beginning the value of KSP as 1.2 10 to the minus fifth, we'll just plug that in and solve. And when we do, x works out to be, in this case, 0.0038. Now, let's summarize. In part A, our solubility was 0.014. In part B, our solubility was 3 times 10 to the negative fourth. And in part C, our solubility is what we just found, 0.0038. Now, which of those solubilities is biggest? Well, by far, the one that's 1.4 times 10 to the negative second. It's an order of magnitude bigger than either of the other two. So your biggest solubility is found in water. Now, why would that be? In parts B and C, we had solutions that had common ions with the salt in question to begin with. So the common ion effect is to reduce solubility. If you start with a solution that does not have water, a solvent that does not have a common ion in it, then you're going to get the biggest solubility possible.